So we are in 3D space, so V, there are actually, it has three components, because the velocity on the x-axis, the velocity on the y-axis, and the velocity on the z-axis. So V is actually, first of all, it's actually V1, V2, and V3, right? It's a vector, V1, V2, and V3. And for each one, for example, U1, of course, is a function of also x, y, z, and t. So this is the velocity. Okay, so velocity of the materials, and we derive two equations. Okay, exactly based on the two conservations. The first one was the first equation was the probably I can write down in a slightly thinner. Okay, cool. Probably this is better. So the first equation that we derived was based on it's actually called the equation of continuity. Equation of continuity. Okay? So this is actually based on the conservation of mass. Conservation of mass. Right? Okay. And this equation, it actually reads partial rho, partial t, plus the divergence of rho multiplied by v that equals to 0. Okay, and the whole idea was that the changing of it. So let's say if we are considering a small piece of space, okay, in our 3D space, then the total amount of mass within this area actually the change at any time point, the change of mass within this small piece of space actually. It can only goes through the inflow and outflow, okay, through the boundary. Okay, so that was the idea of the equation of continuity. And the second equation was the equation of motion. Equation of motion, and that's based on the conservation of momentum. Okay, the conservation of momentum. And the conservation of momentum, we are also talking about. We're not talking about the mass within the space. Okay, within this piece of space anymore. We're actually talking about total momentum within the piece of space. Okay, when we're talking about total momentum. Okay, when we're talking about the total momentum within this piece of space, then again the piece of any change of the momentum, of the total momentum within this piece of space, again, it can only go through the exchange of momentum through the boundary, okay, from the inside, from within this piece of space and without, and outside this piece of space. And we also derived a partial differential equation that was about the velocity, right, which reads partial v over partial t, and plus, okay, the plus v dot product with the gradient of v, and which equals to f, which is the force from external source, and then minus. Okay, probably another way to write this down is probably this is better, and then plus 1 over rho multiply the gradients of p. Okay, p is the pressure, and I'm going to specify this a little bit later. Which equals to and the whole part of this equals to the total force. The external force F. Okay, so let me write down the comments at the end. So this is the external force. And if there are no external force, which is that all the flow, they are just flowing in a certain, let's say, completely freely. Then in this case, the right hand side, of course, is going to be 0, okay? Because there's no external force. But again, there are also in many natural cases, there are actually external force. For example, when we are talking about the water dynamics, okay? For example, the water dynamics in a certain space, and in that case, we have gravity. Right? We have a gravity. Or there are actually external forces, acting upon all the particles or all the pieces of the mass. Okay, just simply because they have mass and they are gravity. Okay, and another case of scenario is that there is a, for example, magnetic flow. Okay, in a magnetic flow and which takes place within a magnetic field. In that case, there is a magnetic force, okay, which is acting upon all pieces of the mass. Okay, but in certain easy case, let's just say there's no external force, there's no field, okay, no external force, and the fluid is flowing through just completely freely. Okay, and in that sense, in that case, we can just set F equals to 0. The P over here is pressure. Okay, and the pressure also comes from the pressure also comes from the density and the mass. Just as we have for example, if you swing and then the pressure that you feel by your ear is actually will be completely different when you are around the surface of the water, or you go 1 meter lower below the water, or 2 meters, or 3 meters. Okay, if you have any diving experiences. And the pressure caused by mass, okay, actually in certain point within the flow, it actually points out everywhere. Okay, it's an internal force and it points out everywhere. Okay, but these two, again, the derivation of these two equations, these were actually not completely trivial. Right, not completely trivial. And it's not our focus today. Our focus of today is that now let's say we now accept these two equations. We just say we accept these two equations, and let's just completely forget, okay, what we have done to deduce these two equations. Now, what can we do to simplify these two equations, okay, to deduce a partial differential equation for the sound? Remember that sound is actually what? Sound is a wave. Okay, so our new target is that we want a PDE for sound. But don't forget that sound is also a wave. So, okay, what we expect, right? I mean, using our reductions. Okay. Before we really do anything, okay, what we expect is again a pure partial differential equation for vibration. Okay, this is what we're going to expect, right? So what we should expect, again, it will be something like, for example, partial rho, the second order. Sorry, let me probably running that another way. So rho tt equals to c square Laplace of rho. Right? This is something that we would expect before we even do anything. But what we are going to do is that we are going to deduce this, okay, from the two equations that we have just deduced, okay, from the just based on Newton's mechanics. Okay. So what we are going to do is, again, we are going to make assumptions. Okay, whenever we want to simplify something, a very complicated model, okay, deduced from the nature, okay, we make assumptions. Now we're going to make assumptions. Again, these assumptions are making our model no more valid, or the more assumptions that we make, okay, the further that we get from the reality. Okay, making this assumption will absolutely make our model further away from the reality, but okay, it will be easy for analysis. It is going to have a very simple form, right? It's going to have a very simple form, which is actually very convenient for us to do computation or to do any analysis. Okay, and the assumption that we're going to make over here, okay, the first assumption, they're actually again going to be multiple assumptions, which if you read the original textbook, is actually again, I mean, they are in different places. They hide in different places, and we need to grab them out. Okay, and so the first assumption that we make over here is that, okay, the rho, okay, it doesn't change much. What does that mean? What does that mean? It's basically the following. Okay, the rho x t, no matter what it is. Okay, no matter what it is, it's mostly okay, a constant. It's mostly a constant, which means that I'm assuming that since we are talking, for example, we are talking about the, for example, the sound, right? The transportation of the sound. This transportation of the sound takes place in the air, and in this case, we are assuming that the density of the air is not changing that much. Okay, it's not changing. It is changing, absolutely changing, but it's not changing very much. And specifically, I'm going to write down the rho as rho 0 plus an epsilon multiplied by rho 1. Okay, here the rho 1 is the changing part. The rho 1 is the changing part, and I'm going to again write it down as x t or rho 1 x y z t. They are equivalent to each other. So let me try to assign these to rho 0 and rho 1. Right. So rho 0 is, you can regard it as the average value of the density of the air, and that probably is not going to change very much because if the density of the air it changes drastically from one place to another, then what you're going to find is that just simply because for example, I move one step further, then I cannot breathe anymore because there's no air here, and I have to, for example, go left for another step for me to breathe again. Okay, and that kind of scenario, although not completely impossible, is very rare. Okay, in reality. Okay, so in this case, just assume that there's a large portion of the density that can be regarded as a constant. Okay, in certain space. However, there are indeed motions of the flow, right? There are indeed motions of the flows. Otherwise, there won't be any sound. There won't be any vibration. There won't be any sound anymore. So there are indeed something that's changing, but that change, the changing part, is actually very small. They're so small as that I am saying that this is on the magnitude of epsilon. Okay, the changing amount of the density of the air, compared to the average amount of the density of the air, that's something very, very small. But it is exactly, it is exactly the small changing over here that brings us the vibration, that brings us the sound. Okay, is that part okay with everyone? Is that right? Okay, that part is okay? Cool. So due to the same reason, my, let me use another part, okay? My v, the velocity, we cannot, since what I was just saying that, the changing amount of the air, the changing amount of the density is actually very small. So in the same reason, I am assuming that my Vt, is also very small. To represent that, in a mathematical fashion, what I'm going to write is that, let's say my V equals to epsilon V1t, V1xt. So so good? So good? Okay. So now let's say, what we're going to do is that, now I have made these assumptions. This is called the small flow, small flow or small change, assumption. Okay, and after I made these two assumptions, what I'm going to do is that I am going to, you see, what I'm going to do is that I am put these two things, back into these two equations. And let's see what will happen. Let's see what will happen. Let's say, so let's first look into the equation of continuity. Let's write the original equation again here. So which is, now, again, the equation of continuity. Equation of continuity. Which is, again, partial rho, partial t, and then plus the divergence of rho v that equals to 0. So that's good. Don't forget, now my rho equals to rho 0 plus epsilon rho 1, and my rho 0 is a constant. My rho 0 is a constant. Okay. So what do I get if I put these two terms into this equation? What do I get? What's happening to partial rho, partial t? What's happening to partial rho, partial t? By partial rho, partial t is going to be partial rho 0 plus epsilon rho 1, right? Partial t. So what happens now? What should I obtain? Come on. Come on, please. Because partial rho 0, partial t is what? Is 0. Rho 0 is a constant. Okay? So what I'm going to get is actually epsilon partial rho 1 partial t. So what's good? Okay? Second term.
Are the epsilons the same that you use, just to be clear?
Say it again.
Are the epsilons the same in velocity and in...
Yes. So yes, that's right. I am assuming these two epsilons are the same. Okay, cool. I mean, on the other hand, it actually would be very hard to imagine that the speed is flowing. I mean, for example, the magnitude of the speed and the changing of the density is completely at two different magnitudes. Right. Actually, it's hard to imagine that. Okay. So this is the first term. What about the second term? The gradient of, the divergence of rho v. What is that? That should be the divergence of what? The divergence of what? Come on, just say it out, please. Rho 0 plus epsilon rho 1, and that stands for my rho, right? And what else? Multiply by epsilon rho v1. The question is that how, well, okay. Of course, the question is that what will happen if I open the bracket? Right, what will happen if I open the bracket? But we also know what? We also know that this is the divergence operator, and this is a first order differential operator, and it is linear, right? Since it is linear, I am granted the access to just simply, for example, break up the sums and also extract the parameters, right? Okay, and so there are going to be two terms. Okay, so well, this is the first time that we are going to do some differential operations, okay, in this class. So let's try to do that a little bit more carefully. Okay. So first of all, of course, there's going to be like rho 0 multiplied by epsilon v1, okay, and then plus epsilon rho 1 multiplied by epsilon v1. Let me erase this. Epsilon v1. So that's good, okay. And then the next thing is that you see epsilon. Epsilon is first of all is a parameter. Also, it is a scalar. It's a scalar, so I can extract it. Okay, it can be passed through all of the multiplications that I want. So over here, in the first term, you see rho 0 is what? Rho 0 is a constant. Epsilon is also a constant. Indeed, that comes out. Okay, so that's actually is going to be epsilon rho 0, and then the gradient, the divergence of v1. Okay, so we're so good. And then the second term, it becomes, you see here's one epsilon, here's another epsilon. So what we're having is actually epsilon squared, and then the gradient of rho 1 multiplied by v1. Is that right? Okay. So this is the first term. This is the first term. And this is the second term. It tells me the whole equation of continuity, it tells me that the first term plus the second term equals to 0. Right? The first term plus the second term equals to 0. So what we are going to do in the next step is actually called the magnitude analysis. Okay, the magnitude analysis. Okay, the magnitude analysis, which is that, you see, on the left-hand side and the right-hand side of this equation, there are terms on different magnitudes. Some of the terms they have, for example, here, epsilon. These terms, they are O epsilon. Okay? This is actually O epsilon. There are also terms on the second magnitude, which is O epsilon squared, right? If I want one equation to hold all the time, because you see, because my epsilon can be arbitrarily small, my epsilon can be arbitrarily small. Well, okay, sorry, not my epsilon can be arbitrarily small, but sorry, this is a process. You see, if I want an equation to get balance on both sides, then what I wish is that on any of the magnitudes, okay, this equation will hold. Otherwise, there are going to be what? There are going to be inconsistencies. Okay. So what we're having over here is that. So let's first extract all the terms, okay, on the magnitude of epsilon. So the magnitude of epsilon, what we are having is that if we're looking into all the terms, okay, with magnitude epsilon, then that's actually epsilon partial rho 1 partial t, and then plus epsilon rho 0 and the divergence of v1, okay, that equals to 0. So far so good? So far so good? Okay. So I can, of course, I can extract and then divide epsilon on both sides. Okay. So this is the new version. This is the new version. This is the new version of equation of continuity. Okay, this is the new version of equation of continuity. Okay, so let's compare these two equations. Let's compare these two equations. Specifically, I'm saying my equation star and my equation star star. Okay, what's the difference? What's the difference between the equation star and the equation star star? The equation star is my old version, it's my original version of the equation of continuity, and my equation star star is the new version of the equation of continuity. What's the difference? Sorry, say it again. The row, okay. That's a very sharp catch. So you see, originally, in my original equation, my equation star, I was having a gradient. I was having a divergence of rho multiplied by v, but don't forget, rho is what? V is what? Both rho and v, they are what kind of variables? Dependent variables, which means that my equation star is what kind of equation? Is it linear or nonlinear? My original equation is a nonlinear equation actually at order 2, right? Because it has a rho, it has a v. Both rho and v, they are dependent variables. Okay. But what about my second equation? What about my equation star star? Rho 0 is what? It's a constant. Therefore, this is actually a constant multiplied with the divergence of a dependent variable. What kind of equation is this? There's a first order linear equation, right? This is actually, the comment is that this is actually comment. Right? Comment. This is first order and linear equation. Okay? This is first order linear equation. In all the time, okay, in all the time of this class, okay, we would be preferring dealing with linear equations because they will be much easier to solve, okay, than non-linear equation ones. Okay, so this is the equation. This is the equation, okay, of continuity. The second one is going to be a little bit more complicated, which is my equation of motion. So again, partial rho over partial t plus the inner product, dot product, okay, with the divergence, the gradient of v, okay, v, and then equals to 1 over negative 1 over rho. So, okay, probably better way. So let's say plus 1 over rho, and then the gradient of P, okay, equals to F. This is my equation of velocity, right? This is my equation of velocity. And in this case, let's assume that the external force F is 0. Okay? So again, you see, this is my second. This is my I have made many assumptions over here. Wait a minute. Where is this my assumption? Where did my assumption go? Okay, this is my this is my first assumption, and then this is my first assumption, and then my second assumption is going to be, so this is my first assumption, and my second assumption is going to be here, because you see, originally this was F, right? This was F and this was P. Okay, they are not directly about anything that we want. Okay, they are not about V, they are not about rho. So the second assumption is about the force. We'll be first assuming that F equals to 0, which is there's no external force. Well, in this case, this is probably not so unnatural, right? I'm just saying. I mean, all the fluid, okay, they are moving just completely freely. And the second thing is that I am assuming that P, okay, is a function of rho. Okay, I am assuming P is a function of rho. It's also it's also not so hard to accept this, right? Of course, I mean, the larger the density, we would expect that there are more particles accumulating at a certain place, right? More particles accumulating at a certain place, and all the particles, they are moving, which means that there will be more collision, right? There will be more collision at these places, right? There will be more collision at these places. And more collisions of the particles will naturally bring up the pressure, okay, the pressure at this place. Because pressure is what? Pressure is that if I place something, for example, if I place my pen into the fluid, okay, then averagely in 1 second, how many particles are going to collide with are going to bump in with my pen for how many times? Okay, that's the physical interpretation. That's actually the physical source of the pressure, right? Okay. So I am assuming that P is a function of rho, and also, okay, this F is usually a monotonically growing, monotonically increasing function. Which is larger the density, larger the pressure. Okay, larger the density, larger the pressure. Okay, so over here, I am very happily to rewrite this equation in the following. Okay, first of all, my F is going to be 0. Okay, no, there's no right answer. And secondly, my T is going to be rewritten into F rho. So now this equation, this is an equation that's only about our two dependent variables, V and rho. Okay? So what can we do for this equation? Again, knowing that, don't forget that I was assuming that rho equals to, my rho can be separated into two scales. Okay, rho, oops, sorry, let me rewrite this. Okay, my rho equals to rho 0 plus epsilon rho 1, and I am assuming that V1, okay, sorry, V equals to the speed, the velocity everywhere is very slow. V equals to epsilon V1. I was assuming these two things. Okay, now what I can do. First of all, my partial V, partial T becomes what? This is actually very straightforward, right? My partial V, partial T becomes what? Rho, actually epsilon can directly comes out, right? Epsilon partial V1 partial T. So is it good? Okay, so it's good. What about the second term? What about the second term? What about the second term? Again, rho V is epsilon V1, and let me just directly put it in, right? Okay, so what I'm getting is actually epsilon, let me finish the ups, so whatever. Epsilon, okay, and then what we have over here is the epsilon V1, okay, and then multiplied by the gradient of epsilon V1. So good? So good? Again, my epsilon is a scalar, a constant scalar. So it can be extracted out. Okay, it can be passed through all the modifications. So what we're having over here is actually the following is actually here, epsilon squared. These two epsilon can come out, right? And then multiply by the V1, okay, multiplied by the gradient of V1. So far so good? So far so good at this point? Okay. Well, let's say, you see, this term is about epsilon. This term is about epsilon squared. What does that mean? This term. The first term, we now, I mean, just with some very straightforward analysis, I know that the first term is on the order of epsilon, and the second term is on the order of epsilon squared. What is it? They are not on the same order. Which one will be much smaller? Which one will be much smaller? But my first term actually is going to be much larger than the second term, right? Which means that when I'm considering all the computations, all the dynamics, okay, on the order of epsilon, this term can just simply go away. Because it's when my epsilon is very, very small, this whole term is going to be very, very small. So small that I can neglect it. So was it good? So was it good? Okay. And actually that's very good for us. Why is that? Why is that very good for us? Because originally, what kind of term is this? This is a nonlinear term. Right? I can just simply throw out the nonlinear term without any cost. Why isn't that good? Right? Okay, is that very good? Now the third term, well, the third term is completely about rho. Okay, so now we will have to, what we will have to is that, okay, so now what we will have to do is to reintroduce, okay, that rho equals to rho 0 plus epsilon rho 1. So this is about, first of all, 1 over rho, it will be rewritten to 1 over rho 0 and then plus, okay, epsilon rho 1. Okay? And then secondly, it's the gradient of f rho 0 plus epsilon rho 1. Right, this is my third term. Of course, what I would like to do is to break it up, okay? Break it up of this term. So if I want to break out this term, what is necessary, what we needed is the Taylor expansion. Taylor expansion. Okay? We'll be needing, so what we're going to expand this term, okay, around rho 0. We're going to expand this term around rho 0 and see what is the term, what is the term on the order of epsilon, what is the term on the order of epsilon squared, and so on and on and on and on. Okay, so this is now left as a small exercise. Let's try to spend about 5 minutes on this. Okay, so this is again, of course, a very tiny quiz. Of course, I'm not going to collect your answer, but this is going to be a very tiny quiz. Okay, about how are you doing with your Calc 1 and Calc 3? Okay, go ahead. So another thing is that I don't need anything that's about order 2. Okay, I don't want to care about anything about epsilon cube. Okay, epsilon squared will be enough. And you don't really have to multiply everything out. Just have a sketch, have an idea about how you are going to do the Taylor expansion. That would be enough. Okay. So which means that you may do the Taylor expansion to 2 different terms. Right? One is the first of all is the fraction, okay? And then another thing is the gradient. Okay, but you can write down everything as the product of 2 Taylor expansions. One Taylor expansion for this, and another Taylor expansion for that. Okay. And neither of these 2 Taylor expansions should have a term that's higher than 2. Okay. Okay, so most of these should be done with the first part, right? So how do I do a Taylor expansion for 1 over rho 0 plus epsilon rho 1? How do I do a Taylor expansion for this? It's going to be around rho 0. It's going to be 1 over rho 0, and then do what? And then minus 1 over rho 0 squared, because again, 1 over x squared, the derivative of 1 over x squared is the negative 1 over x squared. Sorry, well, the derivative of 1 over x is negative. Sorry, then probably 1 over x prime equals negative 1 over x squared. Right? Okay, so for this step, what I have is that, okay, 1 over 0 squared and then multiply by epsilon rho 1. So good? Okay, so there's an epsilon. And all of the rest of the terms is going to be things that are about, including and about order 2. Right? So that's O epsilon squared. Oops. Probably, yes, yeah, okay, this is okay. O epsilon squared. Okay. Anything that's on the order of epsilon squared actually is out of our interest, just like this one. Right? Epsilon squared out of our interest. They are too small for us to look into. Okay? This is the first term. And the second term, what about the gradient of f rho 0 plus epsilon rho 1? What about that? It's actually, well, you see, this is what is gradient. So gradient actually is actually partial f rho 0 plus epsilon rho 1 partial x. It's this. And it will also include the same thing partial y and the same thing partial z. Right? Okay, so let's first look into what is it, okay, in the partial f, partial x. What is it in the partial f, partial x? Okay? So how do you compute the partial f, partial x over here? Knowing that rho 1 is also a function of x. Knowing that rho 1 is also a function of x. So Okay, so I mean, assuming that we can change the order of differentiation, okay, arbitrarily, I mean, as much as we want, then of course it can be written as, for example, first of all, let me try to do a Taylor expansion for f, okay, and then look into what is the partial derivative for the Taylor expansion of f, right? So how do you write down the Taylor expansion for f around rho 0? What's the Taylor expansion for f?
F rho 0
Okay, well, f rho 0, and then what?
plus F prime rho 0.
Plus epsilon f prime rho 0. Actually, you're right. Actually, it's f prime rho 0 multiplied by epsilon rho 1, right? And then the next term is going to be f prime prime rho 0 and then epsilon rho 1 squared, right? But again, and plus the higher order terms. But again, since the epsilon squared term, we don't care about anything. Okay, we don't need to care about anything. So far so good? Okay. And so this is the first Taylor expansion, and then what we're going to do is that we are going to take the partial derivative for any single term in the Taylor expansion. Well, what is that? What is that? F rho 0, partial f rho 0, partial x is what? Partial f rho 0. Sorry, partial f rho, partial f rho 0, partial x. So the first term is going to be partial f rho 0, partial x, right? And then plus partial f prime rho 0, epsilon rho 1 over partial x, and then plus all the higher order terms which are not here, right? What is the first term? What is the first term? Why it is 0? Why it is 0? Rho 0 is a constant. Therefore, f minus f rho 0 is also a constant. Okay, partial constant and partial x, of course, that's 0. Right? So this term is 0. And the second term, what can I do to simplify the second term? You see, again, rho 0 is a constant, f 0 is a constant, f prime 0 is also a constant. Right? F prime 0 is also a constant because it's the f prime x evaluated at f 0, right? Okay, it evaluated at rho 0. And also, my epsilon is also a constant. Both of them can come out. Therefore, what I obtain over here is going to be, finally, it's going to be, okay, f prime rho 0 multiplied by epsilon and then partial rho 1 partial x. So far so good. So far so good. You see, the first two terms, they have nothing about x. They are not relevant to x. What does it mean? That means that if I want to repeat this for partial y and partial z, these two terms, they will bump up again. These terms will bump up again. So to conclude a little bit, you see, it tells me that partial f rho 0 plus epsilon rho 1, okay, partial x, it equals to, equals to this, and then multiplied by the higher order terms. And the same thing is going to happen for my the same thing is going to happen for my partial f rho 0 plus epsilon rho 1, okay, partial y. I'm going to get exactly the same terms, rho 0 multiplied by epsilon, but here it's going to be what? Partial rho 1, partial what? Partial 1, right? And then plus all the higher order terms. Same thing, partial f rho 0 plus epsilon rho 1, okay, partial z is going to be what? Okay, now you can tell me what is that? What is that? F prime rho 0, epsilon, and then partial rho 1, partial z. Right? And then plus all the higher order terms.
Did we lose the gradient on purpose? The nabla?
Yes. This is going to be because what I was doing this, right?
The partial derivative.
I was doing the nabla of f.
Right.
Okay. So finally, this in all, okay, it tells me that the nabla, okay, the nabla of f rho 0 plus epsilon rho 1, okay, it actually exactly equals to f prime rho 0 multiplied by epsilon and then multiply, you see, this is partial rho 1, partial x, partial rho 1, partial y, partial rho 1, partial z. And if they compose a vector, what is that? Exactly the gradient of rho, right? Exactly the gradient. So this guy actually equals to, okay, equals to f prime rho 0 epsilon, okay, and then multiplied by the gradient of rho, and then plus all the higher order terms. Well, actually, O epsilon squared, right? So, what are we looking to? We're actually looking to their product. We're actually looking to their product. We're actually into the product of these two terms after the Taylor expansion, right? So, which orders are in this product? Which orders are in this product? Of course, most of these are higher order terms, but these higher order terms we don't really care, right? We don't really care. So what we're having is that you see 1 over rho multiplied by this term. What I can get? This is going to be a term on order epsilon because there's an epsilon. What about this term multiplied by this term? We have an epsilon over here, and we are having another epsilon over here. So the product between these two terms are going to be O epsilon squared, right? Again, it becomes a higher order term that we do over here. Higher order terms multiplied by this, again, higher order terms. Higher order terms multiplied by these things, again, higher order terms that we do over here. So finally, to conclude, what we do care is this multiplied by this, okay, which means that their product is approximately, okay, 1 over rho 0, well actually f prime rho 0 over rho 0 multiplied by the gradient, sorry, this is actually should be rho 1, right, the gradient of rho 1, let me check if that is rho 1 indeed. Yes, this is indeed rho 1, okay, rho 1, and then with an epsilon over here. So that's so good. So finally, you see how many terms have we considered? This term, partial v, partial t, it gives us an epsilon rho v1, epsilon partial v1 partial t, right? The second term gives a higher order term that we do not care, goes to 0. Okay. The third term after double Taylor expansion, okay, finally it spits out a term that is, okay, epsilon multiplied by f prime rho 0 over rho 0, okay, and then multiplied by the gradient of rho 1. Okay, that's also a term on the order of epsilon, right? Therefore, finally, my simplified equation of motion, okay, my simplified equation of motion becomes the following. It becomes partial v1, okay, partial t epsilon, okay, and then plus f prime rho 0 over rho 0, and then the gradient, nabla, okay, rho 1 equals to 0. This is my simplified equation of motion. Again, what kind of equation is this? What kind of equation is this? Linear, right? Again, linear, because no matter f prime rho 0 and rho 0 actually they're constants. Right? They're constants. Therefore, order 1 linear is linear equation. Okay, so now don't forget that we were looking at two equations, right? So we started from, you see what did we start from? We started from equation of continuity and the equation of motion, right? The simplified equation of continuity is this. And the simplified equation of motion is this. And let's try to write them together, okay? The new simplified system is exactly the following, okay? First of all, the simplified equation of motion, okay, sorry, here's an epsilon. The simplified equation of motion, well, if I get rid of the you consider epsilon in both terms. So if I get rid of both of them, okay, what I have is partial v1, okay, over partial t plus f prime row 0, okay, and then row 1, which equals to 0, okay? And also, the simplified equation of continuity, that is actually partial row 1, partial t, and then plus row 0 multiplied by the divergence of v1. Okay, the divergence of v1, that equals to 0. Okay. Well, based on these two equations, can we give a closed equation that's only about row 1? You see, again, my row 1 is the new dependent variable of density, and my v1 is the new dependent variable of velocity, right? Based on these two equations, can I create a new equation that's only about row 1, not about v1 anymore? Can we do that? What should I do? You see, the first equation, it involves a divergence of v1. And the second equation it doesn't directly tell me what is it for the divergence of v1, but it tells me about the time derivative of v1, right? Okay, so what does that mean? So what about, you see, because the first equation has no partial t for v1. So what I can do over here is that for the first equation, let's try to take the partial t. Okay, this is my new, let's say my equation star, star, star. Okay. Now my equation star, star, star. Now let's say I'm taking the time derivative on both sides. Same as the right hand side is 0, the time derivative is still 0. Okay, so take partial t. I'm going to take partial t on both sides. So first of all, row 1t now it becomes what? Row 1t now becomes what? Row 1tt. Row 1tt, right? And then plus row 0, and now it's partial t, the divergence of v1. Divergence of v1. So far so good? Okay. And again, we are entitled to do anything, to just simply flip out all the orders of differentiation or integration in this class. Okay? So now what we have is that, now what I'm going to first do is that I will first, because here is that we first take the gradient, then, we first take the divergence, then we do the time derivative, but I'm going to reverse the order. I'm first going to do the time derivative, and then take the divergence. Okay? So now what we are having is that row 1 tt, okay, plus row 0. Now it's going to be the divergence of partial v1 partial t. Okay, now the second equation, which is my equation star, 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 star. Okay. Okay, now my equation star, 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 star will get involved because it's exactly about partial v1 partial t. Okay, it is exactly about partial v1 partial t. And this equation, if I plug it in, this equation will become row 1 tt and then plus row 0, and then the divergence of, okay, plug this in, it's going to be, okay, it's going to be f prime row 0, and the gradient of row 1. Well, actually negative, right? Negative. Well, which are parameters that we can extract instantly? Negative, that can goes out. F primes row 0 and over row 0, these are also constants that can go out. Okay, so these things will go out. And you see, here's a row 0, here's a row 0, so they can cancel with each other. So what we really have over here, again, the first thing is row 1 tt, and then plus, okay. Well, actually, the plus will now become minus because due to the negative sign. Okay, minus f prime row 0. Okay, and the other two row zeros they will cancel up. They will cancel each other. So what is left over here will be the exactly this reads, okay, this reads the divergence of the gradient of rho 1, okay, right? This calls the divergence of the gradient of rho 1, and this is exactly the definition of Laplace, right? This is exactly the definition of Laplace, and this is exactly rho 1 tt minus f prime rho 0, okay, Laplace rho 1 equals to 0. Or rho 1, partial rho 1, partial t squared equals to f prime rho 0, okay, the Laplace of rho 1. Indeed, this is a, what kind of equation? Equation of vibration, right? It's the equation of vibration. Okay, let's take a 5 minutes break, and then we'll return with some remaining issues, okay, of this equation.哪里写的不严谨啊？
没有黑板上我这上面。
哦 ，OK OK，你说这个这是上面哪地方没写对吗？
偶然的会有些 scalar 乘法是。
哦，那个好吧，那个我一会儿再强调一下，就是那个 scalar 什么时候是 gradient， 什么时候是 divergence。对我有时候念可能会念错，但是写应该是对的。
我还是觉得加起来就是 divergence。不是，它有的时候加起来就比加起来但是我觉得是这个所以它正好有两个三角形，那这个是带点的，带点是 divergence， 不带点的是 gradient。按定义说是的。其实这个跟带 CVS FOLD 是不一定的，但是它有点不知道怎么导出来会很麻烦，这种东西。就是它导出一大排数据会不停的在后面冒完之后就是那个 spider 装不下，我需要找那个他自己的那个 ID 啊，对吧？装，然后把满的一排做后天配置，造个后。你意思说是数量？就是代码，它会跑这里，然后一跑没有，比如说你看 spider 是对应南面的，对于跑没有跑不到，怎么样跑？这个代码会跑很多出来，然后跑完之后那个前面上到了，怎么会跑很多出来呢？你不要看结果呀，你又不是难道就是分析吗？你不可以分析吗？它不是说你跟它耗一下，它确实会出那么多东西啊。你们写的什么鬼代码啊？去！不是，这不是我们写，之前我自己那个跟一个老师 会出的那些东西，比如说，不是，其实你也就是如果你想 print 你就 print，但我觉得还是 print 出来好看一点。如果不 print， 我也不知道是什么东西。
其实
我当时算的是那个，
就是 Spider 是可以直接查看 variable 长什么样子的。就你既然都已经直接点一下知道它长什么样，就是你一定要
比如说一个特别大的一个矩阵，比如说3000 K， 就是
Python 是可以运10万以上的函数的。我之前就跑过半个小时才出结果。
我知道，我那个一大群我跑了1个小时。
对啊。
对，但是我想看到它是什么东西，因为而且它有的时候还真的看不到，因为它到时候就中间给你写省略号。
就是你不是每个数据都要看啊，你可以点那个 head， 就是你 slice 嘛，就是你想看哪个就把 slice 出来就行。而且那个你直接点那个 variable， 它就不会显示 icon 嘛。
就是我当时对这个文件怎么用那个 Python 处理，还不是很了解，我想每个都是。然后就这个。
行，反正是操作上的问题，那我这帮不了。
后来我去电脑插个电瓶幕电就是想着开着插电屏幕不能关闭，然后第二天早上6点钟起看，好了，快跑完了，
就是你们还给自己就是整一个进度，然后跑一条冒一个出来，跑一条冒一个出来。那怪不得你这肯定出问题。我当时就是我当时做，
我后来已经彻底放弃 Spider 了，因为我想看到全部代码在一个界面上，我真的就把它最开始的 ID 拿去找。然后想了想，
你为什么要看到全部代码？我很好奇。
因为那个东西你知道，就比如说你等了，比如说等了有4个小时，它跑出一行数字出来。
对。
就是因为我把所有东西都放在一个里面。
哦，那这是你的问题，你的问题。
不是4个小时，我不知道它是电脑都给卡住了还是什么，因为我觉得它给我跑100个，你就冒出一个提示来好不好？那我知道你跑了，你要是真没跑，你在大中国岛再处理你这个，所以我就每
所以说
我给他
走一行你就给他一个
不是每一行每走100个什么东西来着，就算是应该是每跑100个，
因为只有100个路。
就有点的感觉，就是我自己设了一个 track， 然后就再归零，再搞混出来一个东西。100个嘛，我说100个够了吧？我说200个我等不了，我等1分钟你给我冒出一个东西来，告诉我，让我知道你还在干活。
就是我真的很懂，就我之前就是期末自己当时数据不多，也就只有10万个，然后当时就半个小时，
数据不多只有10万个，
已经够好了，拜托。然后那个跑了半个小时才出结果，然后关键是有些时候我那个代码是错的，就是你知道自己跑，然后有些时候跑半个小时然后出来一个 bug， 然后那个心情真的是要崩溃。
我就在想，我能把它一个数据包给分成2个。
Okay, so let's get back. And so there's something that I should clarify. Okay, about. I mean, this is I understand this should be. Sorry, I understand that this should be standard materials for Code 3. But since there is a too long time, probably I forgot that. Okay, so what I'm going to say is that this of something and of something, okay, or this something, and this was the dot of something. That's completely two different things. Okay, and this one is called the gradient. Okay, and this guy is called, sorry, can't see this again. Is better? Hope so, okay. And this guy is called the divergence. Okay, this guy is called the divergence. And so the gradient of something will absolutely speed up, okay, a vector. So for example, rho is a scalar. Rho is a scalar. So let's say rho is a scalar, and now my v is a vector. Okay, v is a 3D vector. So the gradient of the scalar will return rho x, rho y, and rho z. Okay, and the divergence of something. Okay, this something has to be a vector. Okay, this something it has to be a vector, and therefore this something. I mean, because this is what the dot here it actually represents the inner product. Okay, so whenever you see an inner product, before the inner product it has to be a vector, and after the inner product it also has to be a vector. Okay. After the inner product, there's something. It has to be a vector. It can't be anything else. Okay. It has to be first of all, it has to be a vector, and then the nabla sign over here, it also represents a vector. What vector? The operator vector. Okay, the operator vector. This is the operator, okay, partial x, partial y, partial z. This is the so-called the operator vector. Okay, so for example, if I am having a v over here, if I'm having v over here as the something, okay, if I'm having the v over here as the something, okay, when I'm having the v over here as the something, then it has to be the partial. It has to be let me see. Okay, it has to be the partial x. Okay, the partial x v1. Okay, and the partial y v. Oh, okay. So I have to use v1 and v2. Sorry. The partial x v. So let's see. Okay, so let's say my v is my v1. Yes, here v1, v2, and v3. Okay, according to this one. Okay, v1 and then v2 and then v3. Okay, my v1, v2, and v3. And the final answer for this, okay, because it is the inner product. So what's going to be? It's going to be the partial x action upon v1, partial y action upon v2, and partial z action upon v3. Okay, this is the so-called divergence. Okay, this is the so-called divergence. These are two different things. And in case you want to verify this, okay, so what we're having here, this actually, here is the inner product. So this actually reads what? This actually reads the divergence of what? The divergence of the gradient of rho 1. Okay, so if you want to verify that this indeed gives us a Laplace operator, a Laplacian of rho 1, then actually we can redo the computation, of course. Oops. So we can redo the computation over here, right? So what we're having is exactly trying to compute the divergence of a inner product, the Laplace of rho 1 and rho doesn't really matter. Okay, the divergence of the gradient of rho. So first of all, what's the gradient of rho? What is the gradient of rho? So, well, again, the inner product, what is the gradient of rho? It's a vector, right? It's a vector of rho x, rho y, rho z, right? The rho x, rho y, rho z here, it represents the partial rho, partial x, partial rho, partial y, partial rho, partial z, right? And then the gradient, well, now partial x, partial y, partial z, the operator vector, it acts upon this vector, so it's going to be an inner product, right? It's going to be an inner product of partial x, partial y, and partial z, okay? And then inner product with rho x, rho y, and rho z, right? The inner product then, of course, is going to be partial x action upon rho x, so it's going to be rho x x. Oops, sorry. It's going to be rho x x, and then partial y action upon rho y, and then rho y y, same reason, and then plus rho z z. This is in Laplace. Okay, so good. So this is the how Laplace is defined. But there's another issue. Okay, there is another issue, which is if you go to read section 30.2 carefully, is that later it also tries to derive. Okay, later it also tries to derive a partial differential equation for v. Okay, it also tries to derive a partial differential equation for v, and its goal, of course, is also partial v. Okay, v1 over partial the second order derivative of partial v1 time derivative. Okay, that equals to f prime rho 0. Okay, the Laplace of v1. Okay, the Laplace of v1. Then again, the question comes, right? How do you do? First of all, how do you interpret the Laplace of v1? Because now it's not a Laplace of a vector, right? It's not a Laplace of a scalar anymore. It's not a Laplace of a vector. And I don't have more time to get into this, but in the derivation, there's one step that you should really notice, which is that so it reads this is the gradient of the divergence of V, okay, this guy, it doesn't equals to the Laplace of V. Okay? This guy, it really doesn't equals to the Laplace of V. It actually has to add up a curl multiplied by a curl of V to complete the Laplace of V. Okay, but I'm not going any further on this direction. Okay, therefore, if you also want to deduce, so this equation, okay, this equation is already valid. We already have it with all the assumptions that we obtain. Okay, but if you want to obtain a similar vibrating equation, okay, for V as well, then actually one thing that we need is to assume that the curl of V, which writes as the outer product, okay, between the nabla and V, okay, we also need to assume this guy equals to 0. Okay, which means that initially, we're assuming that initially the completing velocity field, it has no curl at all. Okay, it has no curl at all, so there's no spiral. There's no spiral in the velocity field. Okay, so that's a comment on this, but I don't plan to go any further because of this will, verify this. The job should be your Calc 3 teachers, not mine. Okay, so if you are uncertain about this part, okay, you should go back to refer to your earlier notes. Okay, but I will be focused on this. Okay, and this is, of course, this is indeed the equation of our rho. Okay, this guy is indeed a partial differential equation for vibration. Okay, for vibration for rho 1. And let's try to review how do we get to it. Okay, this is actually a long journey, quite a journey, right? First of all, we deduced, okay, the equation of continuity and the equation of motion. These two things were based on what? Just two conservation laws. Conservation of mass plus the conservation of momentum. Okay, that's basically saying that if you think that the Newton's mechanics is fine, is correct, then you can have this. And you can have this. Of course, there's another assumption that the physical world is infinitely divisible. Okay, there's no such thing as atom or molecular. Okay, there are no such things as the basic units of materials. No. Okay, the whole world is infinitely divisible. Therefore, we can talk about the things like infinite small, okay, or the derivative of mass, of rho, or the density. Okay, and then to derive, but these two equations, they are nonlinear. Okay, and they are very hard to solve. They are very hard to simulate. Therefore, to obtain a simpler version, what we did here, okay, what we did is that we made another assumption, which is the small flow assumption or the small change assumption. Basically, assuming that, okay, the air density is almost a constant, but plus some small perturbations, which is the rho 1 as the small perturbations. Therefore, the speed of the flow or the velocity v is also on the order of epsilon. Okay, it's also on the order of epsilon. And this method is also called linearization. Okay, linearization, because originally the set of equation was nonlinear, but after the linearization, what I obtained finally was a set of linear equations. It is also called linearization. Okay, and based on these two assumptions, and also that assuming that the pressure, the external force is 0, and the pressure is a function that's only about the density rho. Okay, based on these two new introduced assumptions, finally we arrive at the new simplified system. Okay, which is a set of linear equations. Okay, that's about the rho 1, okay, which is the small perturbation of the density, and v1, okay, which is the speed. Okay, and finally we arrive at this equation. Okay, so partial rho 1, the second order time derivative of rho 1 exactly equals to the Laplace of rho 1 multiplied by a constant, which is f prime p0. The last remaining issue of this equation I would like to talk about is exactly about this constant f prime p0. Sorry, f prime rho 0. F prime rho 0. Well, if you still remember, or if you can check your earlier notes, in the equation of vibration, what was the constant that we wrote over here? What was the constant that we wrote over here? C squared. What does C mean? Originally, we were writing something like C squared, right? What's the physical interpretation of C? What's the physical interpretation of C? Wave speed.
Oh,
Wave speed. Wave speed. Right? Then the question is that why my f prime p0 should be a square of wave speed? Should be the square of wave speed, because let's try to recall what is f prime 0. What is f? What is f? F is the pressure, right? F is the pressure. We assume that pressure is a function that only depends on the density. F prime 0 is that how that pressure is changing, okay, around rho 0, which is exactly around the averaged density, for example, of the air, right? Because of what? There are wave speed in the air, which is about 300 meters per second, if my memory is correct. Okay? There are also speed of sound. For example, in speed, in the ground. Well, of course, there is no speed of sound in vacuum because there is no air, so no speed, but no motion, right? Okay. But so it's actually the first comment I would like to make is that, you see, f prime rho 0, that is a function. This is something. This is a property. It's actually an intrinsic property. Okay, it's actually an intrinsic property of the fluid. Okay, I'm concerning. It's an intrinsic property of the fluid that I'm concerning, right? Because the F, the rho 0, they only depends on the fluid, nothing else. And the second thing is that the unit, we talked about the unit analysis in the class, the unit of F prime rho 0, okay, that's indeed the square of the speed. Okay, how do we see that? Can any one of you try to do a analysis of the unit for f prime rho 0?
N to the power 4.
So that's actually df of d rho, right? Okay. So what is the, first of all, what is the well, df over d rho? That's actually f is what? F is pressure. So that's actually dp over d rho. And the unit is completely the same as p over rho. Okay? First of all, what is the unit for p? P is pressure. So that should be Newton over meter squared. Okay? So that's Newton over meter squared. What about the unit for rho? That's density. So that's a kilogram. Okay? Kilogram over what? Meter cube. Meters cube. Okay. So now, but N is what? F is what? Newton is what? F equals to NA. Right. Don't forget F equals to NA. Right. So that's actually kilogram. Kilogram multiplied by what? Meter over second squared. Right. So here is actually kilogram multiplied by meter over second square. Okay, over meter square. Okay, now over kilogram, and I'm multiplying meter square, meter cube. Okay, on both sides, meter cube on both sides, right? So what I'm indeed having here, let's say cancel, and then here cancel, here this will cancel to first order. So finally we get meter squared over second square. So that's indeed, okay, C squared. Okay, so this is the last count for the the derivation of a partial differential equation for a sound. Okay, that completes my discussion. Okay, so for the last 40 minutes, okay, for the last 40 minutes, I would like to introduce 1.5. Okay, go back from chapter 13 and go back to chapter 1. 1.5. So for the last 40 minutes, there will be not so, again, people are tired, I'm tired as well, so it's not going to be many, it's not going to be that many analysis, okay? It's not going to be computations, it's going to be more about the introduction to concepts, okay? And what I'm going to introduce on 1.4, that's the sort of well-posedness. Oops, sorry.
I think we did 1.5, right?
1.5, yes, you're right, 1.5, absolutely. 1.5, well-posedness. Or well-posed problems. I will be first introducing the idea, okay, of the well-posed problems, and then we are going to talk about why mathematicians care about these things, okay? Let's say, no matter when we are talking about the partial differential equation, okay, no matter when we are talking about general the partial differential equation, which is f, a big function of things like, okay, x, y, z, okay, things about this, these are the independent variables, right? And then the u, v, okay, these are the dependent variables, right? And then ux, right? ux, uy, uz, vx, vy, vz, these are the first order derivatives, and then about uxx, uyy, okay, these are second order derivatives and more order derivatives, okay? A big function of all these things, okay, included together is 0. This is the most general form of a partial differential equation, right? And since there are unknown independent variables like u and v, this kind of things, we will have to solve them. We will have to solve them. And therefore, if we can finally untackle the problem and saying that u equals to 1 over 1 and v equals to 1 over 1 and then or w equals to blah blah blah. Okay, if we can finally untackle these problems, then this is called a solution. Solution to the PDE. Okay, solution to the PDE. And regarding the solution to the PDE, okay, regarding the solution of the PDE, its properties, okay, its properties are exactly about the so-called well-posedness, okay, are exactly about the well-posedness. Or more formally, okay, the well-posedness is talking about a PDE in a domain, okay, a partial differential equation in a domain D, okay, in a domain D, such that, and with a set of initial conditions, this domain D is with a set of initial conditions, and boundary conditions, okay, or other auxiliary conditions, such that their solution, okay, these solutions, they should satisfy the following. Property 1 is the existence. Okay? The existence is that there exist at least one solution, which is the UVW. A choice of the UVW, or let's say, to make it a little bit simpler, let's say there only exists, let's say, one variable, one dependent variable, which is U. Okay. Then in this case, okay, if only one dependent variable U, okay, there exists at least one solution U, okay, including x, y, z, all the conditions, such that it satisfies all the conditions. Okay, so that's to say, it's not only satisfy this equation, but they also satisfy all the given initial conditions or the boundary conditions. Okay, this is the property 1. Property number 2, uniqueness. Okay, which is that there is at most one solution. So what does the existence plus uniqueness talks about? There exists and only exists one solution. Satisfy the equation and all the auxiliary stuff. Okay, right. And the last property is that this solution, okay, this solution uxt, this solution u, okay, it depends on the data, or let's say it depends on the initial conditions, and the boundary conditions. I'm just writing IC and BC. They are short for initial conditions and boundary conditions. Okay, that depends on the initial conditions and boundary conditions and parameters. Parameters are whatever it is in the coefficients for this equation. Okay, on the parameters in a stable manner. In a stable manner. That means what? That means that if for example, if my initial condition changes a little bit, there should be only a small change in my solution. If my boundary conditions changes only a little bit, there is also only a small change, okay, in my solution. If the coefficients in the equation changes a little bit, there is only a very small change, okay, in my solution. This is called stability. This is called stability. So if the solution of a partial differential equation, okay, and plus the initial and boundary conditions, if the solutions of such a problem, okay, exist and satisfy the three properties, all the three properties that we give over here, then we say that this problem is a well-posed problem, or we say that there is well-posedness for this partial differential equation problem. Okay, they are well-posed. And in the field of different partial differential equation, then there are actually many fundamental studies about what class of partial differential equations are well-posed, what part of equations are not, because we are in the field of linear equations, but in the nonlinear field, okay, there can be many cases that a equation is not well-posed, like not the solution, for example, the solution doesn't exist, or the solution exists but there are multiple solutions that are exactly the same equation, okay, or that the equation are actually depending on the parameters and the conditions in an unstable manner, So let me now let me give the rationale. Okay, now let me, because this is the last 30 minutes is going to be more about the ideas. Okay, so it's more about understanding instead of computations. Okay, so I'm now talking about rationales and examples. Because we might be able to. The reason that we are going to talk about that, we are going to talk about rationale, is that because for now I don't have a formal mathematical description for these three conditions or for these three properties for you. The reason is that, you see, for example, for the stability, when I'm saying that it's depending on other things in a stable manner. Well, how do you want to describe that? When I'm saying a small change in the parameter or small change in the boundary conditions, the small change in the boundary conditions lead to a small change of the solution. How do you justify the small change, right? Then actually, if we really want to do that, actually we need a course that's called the functional analysis. That what tells you how to measure the distances or the differences between two functions in the space of the function. Then we will be able to implement metric. Okay, just like we are implementing metric in the 3D space, in the 1D space, in the 2D space, we can also implement metric, okay, in the function space. Okay, but here we won't be able to do that, and this course is not intended for that. So I will only be able to talk about, and we won't be able to rigorously prove anything, okay, for the robustness of any problems. But later, what we are going to do is that we are going to show this. Okay, we are going to show this via computations. Okay, so this is what I'm going to do. I'm going to provide the rationales and examples. Okay, for the robustness from that. So. Again, I have explained in the last few lectures. I mean, there are indeed very solid motivations for people to hope or to expect, right, the partial differential equations to have these properties. And the reason is the following. Okay, for example, for the existence and uniqueness. Again, the partial differential equations, all the partial differential equations that we have seen, they are derived from physics. Right? The logic is that we are using these as models for the realities. Okay, since they are the models, we hope at least the models can give us something, which means that we hope the solution exists. And second, that we hope that the model can since we are using the model to predict, we want our model to clearly give us only one prediction. Otherwise, there will be facing multiple possible futures. Okay, that exactly what the model is not intended for. Right? Okay, so. It is about generally a physical model. In a physical model, we usually expect, or at least we want, the existence and the uniqueness from that. Okay, that's very straightforward to understand. However, the stability. Okay, why do we need such things like stability? Because you see, in the physical world, for example, how do we know that? How do we know the mass of ourselves? How do we know the mass of ourselves? How do we know the mass of yourself?
Okay, scale.
Okay, you step on something, right? Try to see. I'm getting better from yesterday because I ate too much for the dinner yesterday night, right? But that's a measurement telling you that how much kilograms or how much kilograms that you get. But that's only a measure. That only represents, for example, in most of the cases, you're getting a 2-digit number, or 3-digit, or 4 digits. But that has an accuracy. Then this will never tells you exactly how it weighs, how much it weighs. But it's a measure. And any measurements in the physical world, it is going to have a limit. It's limited by the accuracy. Right? Anything that we measure from the physical world, it won't be exactly that, but always come with an error. Therefore, when we are using, when we are using a model to describe the reality, the parameter that we choose, again, they will be measured. They have to be measured from the experiments. They have to be measured from the physical world, right? And these parameters, there will be errors in that. They won't be exactly accurate. So, and the same reason for the initial conditions and the boundary conditions. Okay, mathematicians we can talk about certain functions in finite accuracy. Okay, but not physics, And so that's to say, if we want to use the parameters and the auxiliary conditions, if we want to put them into our model and to evolve our model, of course, we wish that our model will also be okay if these measurements are not exactly correct, because they can't be exactly correct. Right? We'll always hope that my model is robust. My model, it will still give me reasonable results. Okay, if these parameters or the conditions are slightly perturbed. And that's the idea about stability. If there is an error, or for example, on a scale of epsilon, if there is an error in my parameter, which means that my real model should be perturbed for epsilon, in certain parameter or in certain boundary or initial conditions. Okay, then the solution, it also will only change on the order of epsilon, or at least on the order of something. Okay, if I could expect that, then I can say that my model is robust. My model can still work even if these parameters or conditions are not exact. Right? That's the idea. That is the idea of the stability. That is the idea of the stability. But again, it's not always in that way. Okay, it's not always in that way. And let's see. Let me give you an example. Okay, let me give you an example about when that kind of things is no more valid. Okay, when that kind of things is no more valid. And I can give you an example that's actually very familiar to us, and I'm going to use that sample to offend these three properties at the same time. Okay, these three properties at the same time. It's called the following. It's called the n-type diffusion. Okay, before we talk about n-type diffusion, again, what is diffusion? What is diffusion? How we define diffusion in our class? It's a motion that the materials will always flow completely freely from the places with higher densities to lower densities, right? So now, what is anti-diffusion?
Lower to higher.
Lower to higher, okay. The flow will always go from the lower densities to higher densities. So what's good? Okay, so what's good? Well, we already know that, let's say, the diffusion takes the derivative, takes the form of ut equals to, let's say, something like d, okay, uxx. Let's just talk about the diffusions on one dimension, okay? Then what would you expect for the n-type diffusion? What would you expect for the n-type diffusion? Why that is minus sign? Because we expect the flow just go completely reverse, in a reverse fashion, right? In a completely reverse fashion. Okay. That's ut. Okay, that's ut actually equals to minus duxx. So straightforward. Right? This is indeed a partial differential equation. Second, it's a second order because it contains uxx, but still linear. Right? It's still linear. And later you will see that we are actually able to solve it. We're actually able to solve that equation. Solve with the quotation mark. We're not able to give we're seeing the knowledge that we know that we are unable to give an analytical form for that. But we are at least able to have an impression about how does the solution looks like, how does the solution looks like for the anti-diffusion equation. And now let's try to understand why that offends these three conditions at the same time. Why it offends these three conditions at the same time. Existence. Why it may offend existence. Why the solution may not exist. Why the solution may not exist. You see, if I start from an initial condition like this, okay, which means that there's a step. Okay? If I'm starting from an initial condition like this, can you solve this equation forward? Can you do diffusion for that? Of course, there are going to be some problems in u-axis. Of course, right? Definitely, there are going to be problems. But can you imagine a diffusion after? Let's say we start on this, and we keep on diffusion. Can you imagine a process like that? It's okay, right? Just like initially, I have some. Let's say I have some water in the middle, and there's a wall. There's a glass wall, okay, between them. And now I'm just pulling this glass wall away. Okay, then now the water diffuses. Right? We can go forward. But can you imagine going backward, starting from that, and going backward, what will happen?
You can't like undo.
Right? Okay. What does it mean by going backward? Yeah, indeed, right? The lower ones will automatically go to higher positions, right? Where is lower and where is higher? This place is lower. This place is higher. But let's imagine that initially this place already has no water at all. How can we do an anti-diffusion starting from that kind of equation? Starting from that kind of circumstance. It's impossible, right? Because you see, first of all, because you see, at this initial condition, the second order, the u-axis over here is zero, and the u-axis over here is also zero. So if there is any diffusion or anti-diffusion, it can only take place at this place, right? It can only take place at this place. But of course we can imagine that there is a diffusion because there will be water flowing downwards, going backwards. But how do we do any anti-diffusions on that? How can we do any anti-diffusions on that? The u-axis is definitely not zero at this point. So if there are diffusion, there should also be anti-diffusion. But any anti-diffusion is going to violate it. Any anti-diffusion is going to violate a physical law that the density of mass cannot be negative. Because the density of mass over here, they are already, let's say they are already at zero. How can they continuously decrease? That's impossible, right? That's impossible. So in this case, okay, under this kind of initial condition, the solution doesn't exist. Okay, the solution doesn't exist. This is the first thing. Okay, and uniqueness. Okay. Uniqueness is the uniqueness is the following. We all understand that the diffusion is actually a smoothing process, right? The diffusion is actually a smoothing process, and that means that initially there might be bumps. Okay, so let's just say initially there might be for example, I mean, for initial condition there might be some bump, right? There might be bumps everywhere. But after the smoothing process, after the diffusion, we would imagine that things become something like this. Things will be very smooth. Okay, it's okay to, you see, just like when you are having a photo, when you are having a high digital photo, it's actually easy for us to blur it again and again. Okay, to make it more and more blurred. Okay, since we are actually doing diffusion in this case. However, if you are having a blurred photo on your hand, it's actually very hard or almost impossible for us to exactly know what it was initially, right? Because in this case, we're actually trying to unblur the photo, trying to reverse the process and make it from the smooth version going back to the version with a little bumps initially. So far so good? Okay. One last case. Uniqueness. Okay. Oh, sorry, one last case, which is the stability. Let's say even if we don't have the issue of, let's say we are having the solution to this, and let's just say the solution is the solution exists and the solution is unique. Okay, and let's just ignore any problems that may take place. Okay, for the first two problems, the stability is also an issue. You see, imagine that, let's say, initially, I'm having a drop of water, but since I am somebody that's violating all the laws of the Newton's world. So let's say initially, the whole bunch of mass is exactly on one point. It is exactly on one point. Okay, so if I am using a function to represent the original. Okay. So originally, this is not so good. So originally, let's just say my u x 0 when t equals to 0. Okay, it's actually something like this. Okay, something like this. This is the so-called delta function. Okay, this is the so-called delta function. Delta x. Let's say delta x. Then the delta function, it has the property that it is 0 everywhere. It is 0 everywhere, but it is infinity at 0. Okay, the delta function is satisfied the following. Delta x is 0 whenever x doesn't equal to 0, and it is infinity when x equals to 0. Okay, and also delta function also satisfies that the integration, from negative infinity to positive infinity of delta x is exactly 1 dx. Is exactly 1. So far so good? So far so good? Well, we indeed can imagine that initially we are having a delta function over here. And then what's going to happen is that, okay, let me start from a delta function, and then we are going to diffuse. We can diffuse and diffuse and diffuse and diffuse. Okay? Let's say we have diffused for, this delta function, okay, is over here and is diffusing within certain, certain space from 0 to 1, and the boundary is not leaking. Okay, the boundary is not leaking. So what would you expect after a long time? If you are doing a diffusion, what would you expect after a long time? And the diffusion is taking place within a certain space. It cannot go out. It's going to be flat. We would imagine that it's going to be flat. Okay? Of course, this is really long time. But the question is that in any, that means that in any finite time, it's not going to be completely flat, right? In any finite time, it's not going to be completely flat. And that means that in any finite time, it's not going to be completely flat. And what we would expect would be something like this, which is that the place at 0, okay, the place at 0, it has some slightly higher density than the other places. So far so good? Okay. Again, now let's try to reverse. This process. Let's say we started from here. We started from t equals to 0. In the diffusion, okay, in the diffusion process, this is my t equals to 0, and this is my t equals to big T. Okay. Now, if I am starting from this initial condition, in my anti-diffusion process and going backward, what will happen? Okay, it will be accumulate, and finally, everything will be exactly accumulated on what? Finally, the things will exactly be accumulated on this. Okay, let's say this is not 0. This is actually -1. This is -1. Okay, -1, -1. Everything will be exactly accumulated at the place of x equals to 0. But note that this takes place in how much time? Right? How much time has passed if we are undoing the diffusion? Again, let me repeat this logic, okay? When we are starting from the delta function, all the mass accumulates at 0. After time t, okay, I get this. I let the time to go forward. After time t, I get this. Okay? Now I'm doing everything backwardly. I start from this and start to do my anti-diffusion process. Anti-diffusion process. So after time t, what should I exactly get? After time t, what should I exactly? I should get this. I should get back to the initial condition for the diffusion, which is what? Which is the delta function, and the delta function is what? Is an infinity. In this case, we say that this equation blows up. This equation blows up because of what? Because it has infinity in its solution. This equation blows up. Okay? So the first issue is that it will blow up. It will blow up in exactly time t. It will blow up in exactly time t because the time t is exactly what the time has taken when I was going from this equation, from this initial condition to this ending condition. So if I'm flowing everything backwards due to the symmetry, I should obtain exactly the same initial condition, okay, after time t. So good? The first issue is going to be blown up. And the second issue is that, okay, now imagine that, okay, so let me try to use just another color, but instead of another graph, okay? Let's imagine that my initial condition was actually this. It's not centered at 0, but instead it's actually centered at, let's say, negative 0.1. Okay, negative 0.1. And this is actually a delta function, delta x plus 0.1. So again, it is going to be infinity at negative 0.1, and it's going to be 0 everywhere else. Okay. Okay, in this case, after time t, let's say I start a diffusion process. After time t, what would you expect? What would you expect? After time t, what would you expect? It's almost flat, but the density is probably a little bit higher over here, right? The density is probably a little bit higher over here. So we would have a condition, an ending state like this. So what's good? Okay. Here at negative 0.1 is slightly higher than the other places. Okay. Again, you see, due to the same logic, if I'm exactly starting from this red ending state and going backward, doing my anti-diffusion, I should get what? I should get this red in t, right? I should get this red delta function in t, right? But you see, as I said, this is actually after a long time, right? This is after a long time, long enough such that it's actually both of the solutions, both the red one and the black one, they are almost flat. They're almost flat. Therefore, even there are differences between them, actually the differences are pretty small, right? Differences are pretty small. So let's imagine that the ending state of my red one is actually U2, okay, U2x, and the ending state of my black one is actually the U1x. It's actually fair to say that because the diffusion, it targets to wiping out all the differences everywhere. So after a long time t, actually my U2x minus U1x is actually a very small number everywhere. So therefore, it actually equals to certain things like epsilon. Let's call it as epsilon U3x. Okay, what does that mean? That means that when I am trying to solve this anti-diffusion equation, okay, I just need to change, starting from the time t and going backwards on time, okay? I just need to change my initial condition for a tiny bit. I just need to change my initial condition for a tiny bit. For example, I made a very small mistake from black to red because they are so close to each other anyway. I just made a tiny mistake. But after I made this tiny mistake, what's the difference between the answer that I finally solved when I go back to time 0? And it's actually a drastic difference, right? Because one is infinity at 1, and another one is infinity at negative 0.1. Right? So it is also unstable because the solution does not depend on the initial conditions in a very stable manner. It's very unstable. Okay, it creates a drastic error, okay, after we go up from time. Okay, so actually the case of diffusion and non-diffusion is a very useful discussion topic. Okay, that we are actually going to touch again when we go to how to solve the diffusion equations. Okay, but anyway, today's lecture ends now, and don't forget that our homework will due on Wednesday. If you haven't started yet, please prepare to start right now. And I will talk about 1.6. So my original plan was to get into chapter 2. Okay, on our last lecture between the Spring Festival, but probably we can make it a little bit lighter and just talk about one extra lecture about chapter 1, okay, and about 1.6. And I'm going to also post the homework very, let's say, today or tomorrow. Okay? And it's going to do after the spring, after the spring festival. Okay? So don't worry. Okay, so thank you everyone, and any questions, so we can move on to our office.
关键是后面那个他真的是有点他是那个太自由的那个人，就是他不是那个后面的一个不是领导，我知道他加进他不是后面的一个 special 版本的，后面会存在，是吗？他那个我没看，就是他两个题型，他后面是一加 x， 但是在前面是加的，所以他是后面的一个很 special。
对，就是你后面你所说的那个小会加上进入词就是加上后面主题的口式是一样的。然后但是后面
我去改
我把这个关掉啊。